Hello, welcome. This is week 7. Will be a slightly shorter class because not much was covered. Yeah, maybe we just go through what's what and then it will be a short class too, maybe 1 hour or something. We'll do the problems next class onwards. So basically now we are into the heat transfer part. The fluid flow module is over. And now Professor Arnav Bhatta is taking the heat transfer part. So what did he cover? The very basics, fundamentals only he covered. Like what is conduction, what is convection, what is radiation, the modes of heat transfer, right? Then he introduced Fourier's law for convection, the Newton's law of cooling. Again, like convection is because of conduction plus advection. Conduction is a diffusion phenomenon, advection is because of the bulk flow phenomena. When both of them are combined, it is convection. It's always there when there is fluid flow. This is in case of the static system, induction. For instance, a metal slab, you keep one end at one temperature, the other end at another temperature. There'll be a heat flow. And radiation also, we just talked about it basically. The Stefan Boltzmann equation and all that. Maybe we'll go in depth later. Yeah, he solved a problem on conduction. Very simple. In convection, it can be forced convection or free convection, and boiling and condensation. When when there is boiling, condensation, evaporation, you have latent heat. But for these two cases, you have sensible heat. Latent heat is when there is a phase change. For instance, from liquid to gas or from solid to liquid, whatever. There has to be phase change. Temperature doesn't increase, but that energy, whatever you put, it is used for the phase change. Yeah, yeah, this is the Newton's law of cooling. H is the heat transfer coefficient. In Fourier's law, it's like k dt by dx is equal to q, and k is the thermal conductivity. Yeah, so this is Stefan Boltzmann law. Energy goes as T to the power 4, right? All bodies emit radiation at some particular wavelength, and we have things like black body, ideal body, etc. Maybe we'll come to this later. Then, yeah, basically he derived the conduction. Yeah, so these are the few relevant properties like thermal conductivity, kinematic viscosity, density, specific heat, and all. They come in the energy equation. He also derived the heat conduction equation, right? Like similar to the fluid flow, you take a control volume and you see that the heat that enters in all the phases and then exits opposite to those phases. Then you have some heat generation term. Basic, just normal energy balance. In minus out plus generation is equal to whatever increases. Rho Cp dt by dt. It's very simple. It's called the heat diffusion equation. In its generic form. This is the del square operator. Del square plus q dot by mu is equal to 1 by alpha dot t by dot t. Alpha is the thermal diffusivity, having units of meter square per second. It is not derived for the cylindrical and spherical coordinate, but these formulas are given over here. You can check them. Yeah, basically, yeah, just some simple problems on that is all. We'll come to the problems maybe in the next session. Yeah. Okay. My recording is. Yeah. So again, very basic things only I'll be talking about here, based on what was done in the class. So we saw what constitutive relations were, right? Like, they are not from the first principles. They are experimentally observed. For instance, in the fluid flow module, we saw the Newton's law of viscosity, where the stress is proportional to the velocity gradient. The constant of proportionality is the viscosity. So it's tau is equal to mu into dv by dx. So that's a constitutive relationship. for fluid flow. Likewise, we have for heat transfer, which is known as Fourier's law, and we have for mass transfer, which is known as Fick's law. So these are what are known as constitutive relationships. Okay. So in case of from this module onwards, we'll be looking at heat transfer. Okay. Mass transfer anyway, that is not part of this course. It's a very interesting topic because you can see the parallels between fluid flow, heat transfer, mass transfer. But since it's not part of this course, we'll neglect it for the timing. Maybe we can touch upon it later to show some analogy or analog or something. So yeah, let's look at Fourier's law. Right now, from the constitutive relationship for heat transfer, it is what is known as Fourier's law. Like we have Fick's law for mass transfer and Newton's law of viscosity for momentum transfer. So Fourier's law goes like this. This is the heat flux minus K into del T. This is the del operator, right? What is del operator? It's a gradient operator. We saw what is gradient, what is curl, what is divergence, etc. When we saw fluid flow. So gradient is just nothing but, for instance, in Cartesian coordinate, it's dou by x of I cap plus dou by of j cap plus dou by dou z of k cap. Okay, for the Cartesian coordinate. Likewise, we'll have some for the cylindrical and spherical coordinate. It will be a bit different than this form, right? In the theta direction, in the phi direction, etc. Okay, so for instance, del t will be dou t by dou x I cap plus dou t by dou y j cap plus dou t by dou z k cap. Okay, so del t is the gradient of t. K we are saying isotropic. K is the thermal conductivity. This constant of proportionality is K. So what does isotropic mean? I mean, Professor Arna Bhatta he covered this also. So basically what isotropic means is it's independent of direction. It's same in all directions. So what's the opposite of isotropic? It is anisotropic. Okay. For instance, food. Here the K will be different in different directions. And hence the flux will also be different in different directions. Because this is a structure of wood, okay? It's in the form of grains and all. You must have heard about it maybe in your school days. Uh, there is a directional component also. The way the material in the wood is, because of which like it in in some orientations it will have some property, in other orientations, say perpendicular to the original orientation, will have some other value. Okay. Hence the heat flux is different in different directions. So for anisotropic case, I'll just make a note of like these things. There is a tensor. What is a tensor? Tensor is order 2, right? The vector is first order, tensor is second order. We'll have 9 components. We saw the stress tensor in the fluid flow part. So then you'll have to take a dot product. In this case, you'll have to take a dot product of the tensor and the gradient of T that is. So anisotropic means like it'll have K1, K2, 9 different components of thermal conductivity. and dot it with the velocity gradient, temperature gradient. Say I'm taking x1, x2, x3 are the three directions instead of x, y, z. So you can dot it. I mean, this is like a bit advanced, but just giving you an idea, like K can be, in this case, K is isotropic for our case. And I'll just make another small note. Even for anisotropic case, mostly the off-diagonal components are zero, right? So you just have K1. The diagonal components only will be non-zero. The other components are generally zero, even for anisotropic case. Then you'll have, now when you dot it with the temperature gradient, you'll have like Qx is equal to minus K1 dou T by 2x minus K2 dou T by. Okay, here what was del T? Del T was dou T by 2x in the x direction, say Ex direction, dou T by dou y in the Ey direction, dou T by dou z in the Ez direction. We want flux perpendicular to a surface passing through a surface. Say this is Q, this is the normal direction. So flux passing through the surface is just dot the normal and the Q. Okay, same as Q dot N. What is the flux of heat? What's the unit? It's the amount of energy per unit surface area per unit time, right? So it's joule per meter square second per unit area per unit time. And joule by second is nothing but the unit of power or watt, right? So basically, like any flux, this is how flux is defined. Any transfer or transport of some particular Z divided by the area normal to it divided by the time. That's the general area of definition of a flux. So for chemical engineering, like enthalpy is a good representation of energy. Okay, before we come to that, maybe we'll solve a small problem and okay. Let's check. Yeah, see, this is one particular boundary. Sorry, this boundary is at 300 Kelvin. This is at 500 Kelvin. Okay. The temperature profile is 300 plus 200 x square. This is x is equal to 0, and x is equal to 1. So it's like a parabola, right? It's not linear because it's x squared. So at x is equal to 1, it's like 300 plus 200 into 1 square or 500. So now I want you to calculate the question is for this problem, calculate heat flux at the two edges, left and right side. Let's see, at left and right boundary. Assume it's like a normal solid slab, maybe metal slab or something. You know the temperature here, you know the temperature here, you know the file of the temperature. Calculate the heat flux. So how do you do it? So obviously, like it's a conduction problem. You apply Fourier's law. Q is equal to minus k dt by dx. It's a constitutive relationship. We just talked about it, like how it's a what constitutive relationship means, right? Not from the first principles. Okay, experimentally observed. Newton's law of viscosity, Fick's law, Fourier's law, etc. So here we'll apply Fourier's law. So what is it? Q is equal to minus k dt by dx. It's a 1D problem, so it's just dt by dx. Say k is equal to 1 for simplicity's sake. I'm saying k is equal to 1. So what is dt by dx? It's 400x, right? dt by dx is 400x. Therefore, qx is equal to k is equal to 1 minus 1 into 400 or minus 400. Units alone, I don't care. Just an illustrative example. Uh, x. So at the left face, what is it? Qx at 0, x is equal to 0 is minus 400 into 0 is equal to 0, right? Just plugging in the value. Qx at 1 is equal to minus 400 into 1 or minus 400. So that's the solution for this. But we'll see later that this is not a realistic picture, okay? So it's like the fluxes don't match at the two extremes. So that means there is some heat generation also. But here we haven't talked about any heat generation. So when there is no heat generation, generally like the temperature should be linear. But here like it was a parabola, right? So this was just an illustrative example. Application of Fourier's law basically. We'll get into the nitty gritty later. Maybe next class onwards we'll start solving problems like how we did for fluid flow. We'll take some transport problems, maybe it's a conduction through a slab or through a wire. We'll see how to apply the equations of energy, then the boundary conditions to get the velocity temperature profile in this case, right? So yeah, this was an example. So basically now what I want to come to is that for the earlier part, for the derivation of the Navier-Stokes part, what we did that was that we took the momentum balance. So in this case, we'll have to do energy balance, right? And in chemical engineering operations, energy is represented by enthalpy, the heat content of a system, not the internal energy, but the enthalpy. Like you must have come through the term enthalpy in your thermodynamics classes and all. So that's what we'll be using for the heat content. Okay, that's the basic meaning of enthalpy, right? Not example, a representative. Chemical engineering. And what is enthalpy? You can take it as mass into some specific heat into temperature. Okay, so that's the heat content, right? So enthalpy per volume will be mass into specific heat into temperature divided by the volume. or the density into specific heat into temperature. So since like Fourier's law was this, right? Say the y direction, if I'm saying rho t by dou y, we can multiply and divide both sides divided by rho Cp. Rho Cp are constants. So it's something like this, okay? What is this rho Cpt? It's nothing but the enthalpy per unit volume, right? This thing over here. Make a note of rho and Cp. They're constant. Rho Cpt is the enthalpy per unit volume, or the energy concentration. Right? This what is rho K by rho Cp? We'll call it alpha. We'll define it as thermal diffusivity. Okay, so what is the unit of K? Any idea? From the Fourier's law, just check. What's the unit of K? So flux of heat is what? J by meter square by second, or S is watt per meter square. So watt per meter square is the Q. K will have some units. dt by dx is what? Kelvin by meter, right? So meter will get cancelled. So K units will be watt per meter Kelvin, right? I mean, like obviously watt will have the units of power, and rho Cp is like, what is rho Cp? Units. It's a heat content, right? So it's like joule divided by meter cube, because rho is energy heat concentration. So it will be like joule by meter cube. Meter cube Kelvin. So that's a rho Cpt. So rho Cpt will be joule by meter cube. So rho Cp will be joule by meter cube Kelvin. So what's the unit of alpha? Alpha will have units of K. K's units are watt per meter Kelvin into meter cube Kelvin by joule. K cancel. It's meter square. And what is basically joule by second, right? So what is joule by second? So you'll have a second here. So it's meter square per second. That's the unit of alpha. And if you recollect, when we did the kinematic viscosity, that also had units of meter square per second. I also mentioned about binary diffusivity in mass transfer. That also has the unit of meter square per second. So that's how like the transport of heat, mass, and momentum are very similar to each other. All have this diffusivity component, which is responsible for molecular diffusion, with units of meter square per second, right? So we have thermal diffusivity alpha here, which is K by rho Cp. We already went through this kinematic viscosity, and in mass transfer we won't go through it, but we have a binary diffusivity term. All these three have got meter square per second. Like in mass transfer, you'll have something called Stefan Maxwell equation for multi-component mixture. Then for a pseudo binary mixture, like when when you make an approximation that the it's very dilute, or like in the binary mixture, like the pseudo-binary mixture, like one of the components is much lesser than another component, the Stefan-Maxwell equation will simplify into fixed law, right? And in fixed law, like the constant of proportionality will be this DAB or the binary diffusivity. So I'm not going to details of that because we are not going to be doing mass transfer here. But it's a very interesting topic, especially if you want to study mass transfer, chemical reaction engineering and all. The transport in that, very interesting, but that's not part of this course. So I'm just mentioning that we have an equivalent in mass transfer also. All these three have got units of meters per second. So there are some numbers, okay, dimensionless numbers. Like I mean, again, most of them probably are unnecessary, but anyway, I thought I'll mention them. So one is called Prandtl number. It's represented by PR, and it's nu by alpha. Nu is the momentum diffusivity, alpha is the thermal diffusivity. Like that, we have something called Schmidt number. It is momentum diffusivity by binary diffusivity, and Lewis number or Le, thermal diffusivity by binary diffusivity. That is a mass diffusivity. So these are some dimensionless numbers. Like they tell you like which dominates the other term. So since we are not interested in this DAB, that is the mass transfer thing, so we'll be basically limiting ourselves to Prandtl number. But anyway, just some extra information that may be useful for you. So for gases, all these three diffusivities are almost same magnitude wise. Since they're almost same, like Prandtl will be one, Schmidt will be one, Lewis will be one. All these three will be one, right? For gases, approximately one in standard conditions. Yet for common liquids, it's a bit different. The momentum diffusivity is generally higher than the thermal diffusivity. It's much higher than the mass diffusivity. So like our interest should be mainly Prandtl number because like we have studied about momentum diffusivity, we have studied about thermal diffusivity. So when you combine these two, we'll get the Prandtl number. So we'll stick to that. So for gases already we saw that since they're almost equal, Prandtl for gases is equal to 1. Prandtl for liquids, again like maybe extra information, but maybe let's make note of it. Very common, mostly around 10 it will be. Say water or some organic liquid, right? Much less than 1 for liquid metals, much greater than 1 for oils, for lubricants, basically. Yeah, this maybe I just make a note of this because we haven't come across this term, right? DAB. It's called binary diffusivity. Mass transport will come to it. So if this is a gas, right? In gas, like the particles are spread apart. Their molecular distance is quite more. For a liquid, they come close together, right? The interparticular spacing is lesser. So this is gas and this is liquid. For solid, it will be even more tightly packed. The intermolecular distance will further reduce. So basically, for what do you think happens when you go from gas to liquid? Some phase you have, say, some liquid you have, or some substance you have, which is the gaseous phase. To take it to the liquid phase, what happens to the momentum diffusivity, thermal diffusivity, and mass diffusivity? So obviously, when the interparticular spacing gets reduced, the momentum diffusivity or the viscosity will increase, right? It will become there'll be more of a resisting force when you shear them, right? Likewise, thermal conductivity will also increase because there'll be more conduction now. Particles are a bit closer to each other, so conduction will be easier. Thermal diffusivity goes down. Again, I'm not going to, sorry, battery diffusivity or mass transfer thing. I'm not going to discuss this in detail. We'll stick to mu and k. So it increases around 100 times. K increases about 10 times. And this reduces by around 10 to the power 4 times. Okay. Anyway, I think we can take a 5 minutes break now. And not much to cover apart from this. Like we'll be looking at the energy equation and boundary conditions, and after that, I'll wrap up the class. Whatever problems we'll do the next class because sir has just started solving the problems. I think he will take a 1D. I think he has uploaded the content of the next week where he'll be solving the 1D slab equation. Yeah, so once he does that, we'll get a better idea about, and then we can solve more problems. Okay, so let's take a 5 minutes break now. We'll assemble and finish it off and wrap it up for today. Welcome back. So Searle basically solved the heat diffusion equation, right? Yeah, he did not take convection into account or, yeah, just a normal solid volume and what happens in that. Okay, maybe he'll do the convection part later. But for the conservation of energy, like I'll just write the more general form of the equation. Then we'll see what what are the boundary conditions that we can apply, because boundary conditions are very important. You'll see that you've already seen that Fourier's law is like Q is equal to minus k dt by dx. Then you'll have a gradient of that in the energy equation, right? So you see over here, yeah, that's a del square written, right? Q square t by 2x square plus 2 square t by 2y square plus 2 square t by 2z square. It's a second order differential equation, so we'll be needing two boundary conditions. So it's very important to know the boundary conditions, what kind of boundary conditions to apply. And so I think also talked about the Dirichlet boundary condition, the Neumann boundary condition, and the mixed boundary condition. Yeah, so maybe I'll just revise all that. Hmm. Okay. Yeah, this is covered, right? The Dirichlet boundary condition, the Neumann and the mixed boundary condition. The third kind of, that is the mixed. Newton's law of cooling will also come here. So yeah, I'll just explain what they are. So right now we just saw that a very good in chemical engineering operations, a very good measure of the energy is the heat, the enthalpy per unit volume, right? Or the heat content per unit volume, and heat content or enthalpy we defined as rho CPT. So the energy conservation goes like this. It's very similar to the momentum conservation equation. Maybe sir will derive it later, one of the later classes, but I'm just mentioning right now. This is the unsteady term, the convective term. Rhetorically, I'm not writing in terms of three for XYZ. I'm just writing a general vectorial picture. L dot Q, just a diffusion term. Simply generation term actually. Yeah, from Fourier's law, we already know that U is equal to minus K del D. So you plug this Q here, what do we get? So rho and Cp are constants, right? We already made that assumption earlier. So it's rho Cp dot T by dot T. Rho Cp will come out here also. Del dot Tv and Q we just defined as minus K del T. So minus del Q is equal to K del square T plus H. What is del square? Del square is del dot del or Laplacian operator. We already saw what Laplacian is, right, earlier. So in context of stream potential, uh, stream function, etc., right? Laplacian is just this. Okay, so yeah, this term let us further split it. Right? This term. You can write it as rho Cp v dot del T. plus rho Cp V dot ah sorry from vector algebra. And for incompressible case, we know that this is equal to 0. What are we left with? We are left with rho Cp dou T by dou T is rho Cp V dot del T. It is nothing but the substantial derivative, right? So we are basically left with the substantial derivative. We already saw this concept substantial derivative in the fluid flow part. So here also it's there is equal to K del square T plus HV. Divide both sides by rho Cp. So we'll get dou T by dou T is equal to sorry capital dt by dt is equal to K by rho Cp, which is nothing but alpha del square T plus HV by rho Cp. Fine. This we already saw earlier. Alpha K by rho Cp or the thermal diffusivity. Anyway, like we haven't gone into much detail till now in the class, right? So that's only talked about conduction. So the velocity and all, he hasn't considered the velocity of the fluid and all. So I'm just giving a very general picture. So what Sir has basically done is that he has taken steady state and yes, even if you don't take steady state, at least the velocity part won't be there. So the substantial derivative will be just normal derivative. And you will have this alpha del square T plus whatever the heat generation term, right? So yeah, thing is like when you're taking the velocity, how will you get the velocity? So you'll have to solve the continuity equation, you have to solve the momentum conservation equation in all three directions. From there you will get the velocity profile. That velocity, whatever you're getting, that function, you have to plug it in this energy equation. So it will be coupled kind of question, right? Coupled system, like you're coupling the energy equation, momentum equation with the energy equation, then solving it simultaneously. That's what happens. Like when you have to, we'll surely do problems about that in the future. Right now, it may be a bit complicated, that kind of problem, but I definitely have some problems planned for you guys, which we'll do maybe in the third or fourth class, where we look at both velocity as well as temperature. So, like, okay, here are the assumptions like we can take. Pure fluid, constant or uniform properties, negligible viscous dissipation, pressure variation. Viscous dissipation, as we saw, like it goes as mu into velocity gradient square. If you can check the Birdsworth Lightfoot Appendix B, you'll have the viscous dissipation terms. So yeah, these are a bit few of the assumptions. So, but what I'm more interested is that let us look at the boundary conditions. That's what defines our problem. Without them, we can't really solve, right? So, in general, most of the problems that we will consider here, to simplify them, we won't consider any interfacial heat source. Okay. For instance, like that's the interface between a liquid and a gas, right? At the interface, there is no heat source. So that will complicate the problem a lot. We won't consider any bulk flow across the interface, just to keep things simple. Fine. So the first kind of boundary condition that we'll be having is that, see, this is an interface. We already considered that there is no flux in the heat generation in the interface. So this is phase B, this is phase A, this is some interface, okay? This line that I curved line that I'm showing. So this is the normal to that surface. So the first kind of boundary condition, what I'm saying is that, I'll just write it in words. First, is that diffusive flux normal to the interface is continuous across the interface, right? So this normal direction for A and B, it's same. So that's the first kind of boundary condition. And if there was some heat source present, okay, so that would be accounted for like by simply this, say QnP minus QnA, or vice versa, depending on which way the temperature gradient will be there. Some source, okay, but we generally don't take a heat source. Second kind of boundary condition is what is known as the global thermal equilibrium. Okay, this is A, it's B phase. Let us consider 3 points here, okay? 1, 2, and 3. On this side, the temperature is A1. Here it is B1. Point 2, TA2, AB2, TA3, TB3. So what this global thermal equilibrium says is that across the interface on both sides, right, the temperature will be continuous. That is, TA1 will be equal to TB1, TA2 will be equal to TB2, TA3 will be equal to TB3. So that's the global thermal equilibrium. I'm not saying that TA1 is equal to TA2. They may not be same, right? Likewise, TA1 may not be equal to TB2. I'm just saying that TA1 is equal to TB1, TA2 is equal to TB2, TA3 is equal to TB3. All that I'm saying. So it's not necessary that TA1, TA2, TA3 are same, right? So generally, like if you may get a problem like this, okay, some solid here, right, of length L. Sorry, they're not. Image is not good. Picture is not good. So this is some solid. This is some fluid. Okay, say some solid slab surrounded by some air medium or something, and this is in the X direction. Basically, like if I plot the temperature profile, right? This is say L, okay, this particular point. So some temperature profile there. There. So basically, like this is how we'll apply our boundary condition. We'll say from the first part that the heat flux normal to the interface at both sides is same. So basically that will translate to this thing. Say like the thermal heat conductivity in the solid is K1 and the temperature profile is say given by some T1. So it will be like this minus K2 and say the thermal conductivity in the gas phase is K2 and temperature profile is given by T2. So this is what it will reduce to at x is equal to 1. And applying the global thermal equilibrium, like T1 is equal to T2 at. So I'm just giving you an illustrative example of how we apply the boundary condition, right? So this is what like he explained this as Dirichlet and this is Newman boundary condition. So I'm not giving the names here. I'm just trying to explain what happens. So the third kind is like I'll call it the convective boundary condition. So he was talking about Professor Atta. He was talking about heat conduction in a slab and all. Okay, right? But what happens in real life is that you can have a solid here, say like a confined flow, okay, a tube flow or a pipe flow, and some fluid flowing through it. So you may apply some heat flux in here or maintain some temperature here, and velocity of the fluid takes away the heat from that. So like there is both conduction as well as convection, right? Just a fluid say because of fluid there is convection, and because of solid there is conduction. And this is an example of a confined flow. So you'll have both conduction and convection taking place. So you'll have to have another kind of boundary condition. Same can be true, like say you have some solid over here, say some heated metal ball or something, right? And then you some fluid flows around that ball. Okay, this is the fluid. It's an example of an unconfined flow. So these are some practical examples of kinds of flow that we encounter in real life. And for them, like so there's something called cup mix temperature, okay? Or the bulk temperature, the temperature we can also give it as T infinity. So basically cup mix is meant if some liquid flows through some fluid, like you take this in a cup and you take out the average of that. So that's a cup mix temperature. So it's the concept is something like that. So say some fluid represented by B. These are some types of terms that you may come across in the problems. Cup mix temperature or bulk temperature, right? Can be like TB or T infinity, etc. Right? So the boundary condition in this kind of case is like the conduction and convection you have to match. Conduction across the solid and the interface between the solid and the liquid. That is taken away by the flowing liquid, right? Say I have some, I'm representing that boundary as one. So minus k dt by dx at point is nothing but h into t1 minus t. This comes from the Newton's law of cooling. This comes from the Fourier's law, right? And h is what is known as the thermal heat transfer coefficient, right? You can get it from something a number called Nusselt number. We come across these things later. It's a very introductory class, okay? Which is again a function of Reynolds and Prandtl number. Prandtl number already we saw earlier, right? So that fits here, and then this is the third kind of boundary condition, mixed boundary condition or a convective boundary condition. So yeah, I think this is enough because very little was taught in this week. So just to introduce you to this heat transfer part, this good enough, I feel. Next class onwards, we'll be solving problems. We know the boundary conditions now. We know the energy equation. So like we did for the fluid flow, we'll be simply making some assumptions, simplifying those equations, then solving them to get some profile. Then you'll have some constants, and or when you integrate those constants, we'll find by applying the boundary conditions. Right? That's it. Thank you.